were to attempt to drive an AC signal down it, or if we were to attempt to turn the voltage off very rapidly, what would happen? That's got capacitance too. And I think probably as an example about a month ago, I solved for the capacitance of a coaxial cable like this. What I'm going to do is just write down the answer right now. The capacitance per unit length is equal to the dielectric constant divided by 2 log V over A. So if it were empty, epsilon would be 1. So for my coaxial cable now, I've got inductance per unit length and capacitance per unit length. And one of the things that we would be interested in is how that circuit's going to oscillate if we attempt to apply a varying voltage, or we try to snap the voltage off. What's going to happen? Because now I've got an LC oscillator. So the product, L times C, if I did this right, is going to look like it's going to be 1 over C squared times epsilon.
What about, is that over L squared? LC over L squared? Because those are both over L.
Yes, you're right. Yeah. LC per unit length. So now I choose a cable of a certain length. I know its inductance because I can look up the dielectric constant. I know the radii of the inside and the outside of my cable, and I can calculate the LC product for that. And then the oscillation frequency for some length of circuit is going to be 1 over the square root of C. Right? It turns out that this is true. The product LC per unit length is actually true for any set of parallel wires. It doesn't have to be coaxial. I'm not going to prove that, but I'm just going to take a guess. LC per unit length product is true for any parallel wires.
By parallel wires, do you mean wires or one wire where the other is the other wire?
Any conductors which maintain a fixed distance between themselves. So if I had a twisted pair of wires, all right? They're maintaining a constant distance. There's a helix, but there is a constant distance between the two. That would apply, all right? The product LC per unit length will be that for everything. That's cool. Yes?
So when we're doing the problem with a solid conductor in the middle, we would wind up with the same result? Or
I guess so. Yeah, the product has to, but the
Right.
inductance
Well,
will be
right.
different, and the capacitance will be the same. Right?
okay.
How could that be? Am I in frame there? Let me think about that. That's a really good question. I'm going to assert that's true for any pair of parallel wires.
Okay.
Yeah, Ohanian asserts that it's valid for any transmission line consisting of parallel conducting cylinders of arbitrary cross-section, concentric or not. So,
What you
Wow.
say.
That means follows.
Yeah, okay, that would be true. Griffiths, I believe, asserts that it applies to any pair of wires. Even if they're like, but I will have to check. I will check. Let me check. Yes. Okay. But wait, there's more, but I've lost it. Okay, some quick additional things about these nifty things that we call inductors. One is that you can store energy in an inductor. And we can work out how much energy is stored by starting with the current equal to 0 and then building up the current. There are a variety of ways of doing it, but I'm going to do it this way, right? So the potential across an inductor is L I D. I'm only concerned with the magnitude. Right. The power that I'm going to be putting into the inductor in order to build the current, or the power at any instant is equal to the voltage times the current. All right, but I'm only going to get voltage if the current changes. So this is Li di dt. If I want to know the energy that's stored, that's integral d dt. So it is the integral Li di, which is 1/2 Li squared. Yes?
Is there any particular reason you're using little I for current instead of big I?
No.
Okay.
I actually, in other courses, I tend to be careful about this. I try to use little I as the time varying current and capitalize the amplitude. But we're not talking about AC circuits here, and we're not going to be doing anything with AC circuits in this course. So there's no difference in this course between little I and capital I.
Okay.
Except that little I could be mistaken for square root of minus. All right. That's the energy stored. For a solenoid, yeah? What?
P is power.
P is power. That's the energy stored in the magnetic field in a solenoid, in any inductor. But if I think about a solenoid, then I can see, correct. There's going to be a unit system shift on you here, because I wrote this up off the top of my head after having taught physics 2. So I'm going to write in U in MKS, the MKS system, right, stored in a solenoid is 1/2 U0 B squared L times the cross-sectional area of a solenoid. Or
pi.
This is the volume of the solenoid.
Yeah, C over 8 pi.
Oh yeah,
Is
it is. Yeah, just a moment. I'll get there. Okay. But I'll write in these units for the moment. B squared V. And so the energy stored in a solenoid per unit volume is equal to 1/2 U0 B squared, which in CGS units is 1/8 pi B squared.
Or, where'd the C go?
Yeah, there
C
needs
over 8 pi.
Okay.
mu is
Mu
4 pi
not-
over c.
The mu not equivalent 4 pi over C.
Do you assert that's correct, or do I brand it?
We assert that that is correct.
Okay. You get the idea. Rewriting it like this tells us that we should be thinking of this as energy being stored in the magnetic field and not energy stored in the current in the inductor, right? The energy is stored in the field. Yeah. Oh. Okay, so energies in fields. And that brings me to the next idea. Inductor is done.
Fini.
Some housekeeping business for the course right now.
Would you like a
one
broom?
Is that there will be no homework. Okay, no, actually, let me write it down. You're taping? Yeah, okay, come on.
Of course I'm taking.
Exam Thursday. Includes the material for today, but a little bit less than normal because you won't have a homework on it. So inductors will be on the exam, but it won't be a big emphasis. Exam next Thursday, April
5th? No.
4th,
Third,
3rd,
No.
No,
fourth.
fourth.
Okay, fourth.
4th. Monday's the 1st.
April 4 plus or minus 2.
That works.
Yeah, that's good.
Okay? 2.
Plus for this, plus for my.
Really important. We will have a quiz on Monday.
On homework 9 material.
It will be on the homework that you just turned in,
That's homework 9, okay.
okay? Number 3, the topics are getting a little bit out of order, or will be. Not out of order, but not as they appear on the syllabus, because I moved the exam. So some of the material that would have been on Thursday after the exam, I'm going to be doing today and Monday. All right.
And
But the emphasis of the exam will be on topics for which you've had homework and on which you've had quizzes.
And this,
Yes.
a little bit.
And
Are
yes.
the Wednesday office hours going to be a review session?
Sure.
I like this idea.
Okay? So that's housekeeping.
Good.
And I will have to let Brian know there will be an exam review or he will have my head again.
All right. So we have energy stored in fields. And we want to, we should be interested, we will be interested, very interested in a little bit, on how the energy flows around in the fields. One way to think about the energy in the fields, what's happening, is that a field can do work on charge distribution. So the power dissipated in some circuit, or stored in the circuit, is the current density along the field direction, integrated over the whole volume where the field and the current are present. Right? But that field can be complicated and can include some time dependencies. So that's 1 over 4 pi integral over the volume of C, oops, cover my butt, E dot curl H minus E dot dt. dV.
Clearly.
Clearly. Left as an exercise to the student. I can use a vector identity to move things around.
Vector identities
Oh, I
are
know.
good.
I wish I had my hands right now.
Where are they?
Vector identity. Step 1, vector identity. Step 2,
Question mark, question mark.
Faraday's law. Step 3, solution.
You're forgetting the question mark, question mark.
Power is equal to, you're right. Putting that all together, integral of the volume, C, divergence, E cross H,
What? Ohanian doesn't have this in it. E dot the
E dot d d d t.
that's a scalar. That's a vector minus a scalar.
Yeah, it is.
Wait,
Why not?
this is divergence of E cross H.
But I mean up at the top.
Yeah.
Up at the top you've got
Cross product minus a dot product.
Oh, yeah, that thing.
That's a
Ohanian
problem.
doesn't have that
Hello.
as far as I can find.
Doesn't have this term.
Why didn't I get that?
Is this? That's big. LP.
See this in there and use that.
Hello.
Oh, no. Oh,
I don't know what that is.
It might be wrong.
it's close and you should
It's
look.
probably wrong.
I'll get back to our.
I'll get back to you on it.
That's on the bottom.
Okay.
Oh. That might be the name of the episode.
All right.
I don't even know. Is the result right at least?
What?
Is the result right?
It will be. Once you checked it for me. I'm gonna define a new quantity. Well, no, yeah, I am. I'm gonna write a new definition, little u, which is based upon, it's not a new definition. This is based upon what we've already done for energy density. We know we can store energy in electric fields. We know we can store energy in magnetic fields. And so in a dielectric and permeable material, the energy density is E dot D plus E dot H. Total energy density in a medium. So the power
And where are we wrong?
becomes that J dot EdV. Ends up looking like this. The integral over the volume of this I'm pretty sure about because I probably lifted this out of Ohanian. Divergence of E cross H plus U dt. You've got the flow of energy density out of the region, and well, that's the flow of energy density as well. The power that flows in or out has these two sources.
And that's a dV, right?
What?
That's a dV, right? Because it's still a nickel.
Du dt? What do you mean?
You mean
DV.
And the V is the DV.
Oh,
Yeah.
yes.
Okay.
Okay. Which, if I define a new vector, that's not so bad.
So many vectors.
A new vector,
Point
C
it.
over 4 pi, E cross H. This tells me about the flow of energy in the electric and magnetic fields. It's called a pointing vector. It does point in the direction of the flow of electric fields, but it's actually spelled P-O-Y-N-T-I-N-G because it was developed by Poynting, who was a student of Maxwell's. So that's the pointing vector. So I end up with the power flowing through the circuit Not through circuit, sorry. Flowing out of a volume, right? As the divergence of the pointing vector plus pointing vector has dimensions of intensity, power per unit area.
Is that still being integrated over the volume?
Did you drop the integral sign or?
Oh! Yeah, you're absolutely right.
Squared over.
Integrated over the volume is the total power. Okay, I was going to move on to another topic, but actually, I think I'm tired, so we're going to stop early. The next topic would be, I have it here, we could do it, notes are ready. They're posted too, but I'll cover it on Monday. Conservation of momentum. So this was conservation of energy, actually. What flows in, flows out, gets stored, or gets stored. Yeah.
There's a very different derivation to this.